Today we're going to talk about some numerical applications of the singular value decomposition, and in particular we're going to talk about good and bad matrices, not to put a value judgment on it. This is kind of a new thing. It's a numerical application. So here's an example. Suppose I gave you this matrix and I asked you to solve this equation, simple 2x2 linear equation, and well, of course, you solve it by Gaussian elimination, and it's one step. You simply subtract the first guy from the second, and this is an invertible matrix, so the solution is obvious. It's that y is equal to 0 and x is equal to 2. No big deal there. So the solution is, the point is the vector 2, 0. But now what I want to illustrate is, what if I perturb the target vector very slightly? So instead of this, I replace the second guy with 2.001. And of course, in applications, that's the kind of thing that can happen. You can have small errors. And when you do this and you do Gaussian elimination, you get, well, let's see, you get the same matrix here, 0.001, but now the matrix on the right, excuse me, turns out to be 2 and 0.001. And now the solution is different. Now y is forced to be 1, and x is equal to 1. So now the solution is dramatically different. The solution is now 1, 1, and so a tiny little perturbation in B had a dramatic effect on the solution. So that's very unstable. A solution to an equation like this would be unreliable, and tiny changes could cause big errors. And so this is what I view as being bad. I'm going to decree that, here's a definition in quotes, this 2x2 matrix, 1, 1 with this guy here, is bad. Now, I need to make more precise sense of that, but the notion is that it's bad because when you solve equations, they're unstable. Small changes can lead to big errors. So we want to understand why that is and how to tell. So how do you, basically what I want to do is make precise, how do you measure how bad a matrix is, how sensitive to small changes are equations, to how sensitive to small changes in the target vector are these equations. And I want to observe that if you compute the eigenvalues of this matrix, what you get is the following. Let's see, you get lambda squared minus 2 point something times lambda plus 1 point something minus 1. So that's lambda squared minus approximately 2 lambda plus a very small number. And let's see, so what are the eigenvalues of this matrix? Well, you just use the quadratic equation, and let's see, 2 plus or minus the square root of something close to 2 squared minus some tiny number over 2. And so you can more or less ignore this 4 times 0.001. This number here is extremely close to 4. 2.001 squared is extremely close to 4. After you take the square root, it's extremely close to 2. So that says that lambda is very close to, again, I'm just approximating here, lambda is very close to 2 plus or minus 2 over 2, which is to say something very close to 4 over 2, which is 2, and something very close to 0. And again, this is just approximate. I don't want to write down exactly what the decimal is. It's some tiny number. It's not really 0. It's just very small. And that's the problem. So what causes the trouble is when you have very small eigenvalues, or more precisely, what really matters is the ratio of the biggest to the smallest eigenvalue. And in this case, it's on the order of, well, just very big. It's 2 over a tiny number, which is very big, and that's the problem. So that's a way of measuring how bad a matrix is, which is to say how unstable linear equations are going to be. All right, so if A is a square matrix, well, at least if it has real eigenvalues, I have a good measure of this quality, good or bad, of the matrix. You write down the eigenvalues lambda 1 through lambda n, and well, you take their absolute values to make them all positive, since it's only the absolute values that matter, and you look at the ratio of the largest eigenvalue to the smallest, and you say it's bad if that ratio is big. So here's the definition. Suppose A is a square matrix, and it's symmetric. So, of course, since it's symmetric, it has real eigenvalues. And we define the condition number of this matrix to be the ratio of the absolute values of the biggest and the smallest eigenvalues. Now, it's not necessarily positive definite, so it could have some negatives. That's why I have to put in the absolute values. But what matters is the ratio of those absolute values. So that's the condition number of a symmetric matrix. And it's a measure of how good and how bad it is. Good means small condition number, and bad is big. And again, the small condition number says that solving equations AV is equal to B is stable. It's sort of insensitive to perturbations of the vector B. Okay. Well, what if the matrix isn't square? What's the notion? What's the comparable thing? I mean, solving AX is equal to B is something you do all the time, even if A isn't square. And so here's the definition. Suppose A is an m by n matrix for any real matrix for any size, not necessarily square. Then you define the condition number of A as follows. Well, you do the usual thing. You take A transpose A. And what you conclude is that the proper notion is sigma 1 over sigma r, where the sigma 1 through sigma r are the non-zero, are the singular values. And that is to say, what I'm saying is, in other words, what you do is you take this matrix A and you replace it with this matrix A transpose A, which is now symmetric and positive definite. So you can look at its eigenvalues and you can take the lambda max over lambda min. And the condition number of A is the square root of that. So it's the square root of the condition number of this symmetric matrix. That is to say, it's the square root of lambda max over lambda min for the corresponding symmetric matrix. Okay. And I should say that if the matrix is singular, so it has some 0 eigenvalues, then you say that the condition number is infinite. So that's like taking lambda min to be 0, and lambda max over lambda min would then be, so to speak, infinity. All right, so again, let me reiterate why this is the definition of condition number. The point is that if the condition number is small condition number is good. That's definitely sort of the take-home lesson here. And what that means is that solving an equation ax is equal to b it's not too sensitive to small changes in b. And it's clear that having small eigenvalues or small singular values is more or less what you need. Okay, so that's the condition number. Let's move on and talk about our next application of the singular value decomposition. This is a really clever thing called the pseudo-inverse. And what it is, it's a substitute for the inverse of a matrix if you don't really have an inverse, and especially for non-square matrices. Okay, so suppose you have your matrix A and you've given it singular value decomposition P sigma Q transpose. This has a natural inverse, which is the following. If A is an m by n matrix and you take its singular value decomposition, decomposition like this, then the pseudo-inverse of A is defined to be the following. It's written A plus, and it's Q sigma inverse P transpose. Okay, so we'll stare at this for a minute. So it's as if you've taken the transpose of A, because that changes the order and puts in the transposes, except that you've also changed sigma, which is diagonal, to sigma inverse. Okay, and it turns out, we'll show in a minute, that that's not an unreasonable thing to try to use as the sort of inverse to A. And as I said, it's close to A transpose, except that you've got this sigma inverse instead of sigma transpose. But it is the transpose size. If A is m by n, this thing is n by m. And so A plus is an m by m matrix, and A plus A is an n by n matrix. Okay, so let's see if this thing has a chance of being an inverse, or how close it is, or I don't know. Let's see what kind of properties it satisfies. Okay, well, let's see. So we start with our matrix A. This is a misprint. It's really m by n, and A plus is the transpose size. So let's check, what is A times A plus? Well, let's see. A was P sigma Q transpose, and A plus is Q transpose sigma inverse P, excuse me, transpose. So you get Q sigma inverse P transpose. And let's see, this Q transpose Q, that kind of looks like the identity to me. So, but you got to be careful. Q has orthonormal rows, so I'm just going to indicate it schematically like this. And Q transpose has orthonormal rows, and Q, which is its transpose, therefore has orthonormal columns. And so when you write Q transpose Q, you have the columns on the left, rows on the left and columns on the right. And indeed, when you multiply those two things, you do get the identity. So you can cancel those, and you get P sigma sigma inverse P transpose, and sigma inverse really is the inverse of sigma, so you can cancel those, and you get P transpose. And let's do the same thing with P. P has orthonormal columns. P transpose has orthonormal rows. So when you multiply P times P transpose, it doesn't quite work. You're not multiplying the rows and the columns in the right order. So it's not necessarily the case that P transpose is the identity. But that's not bad. A lot of stuff canceled. And in particular, if you look at what A plus is, you get, to summarize what I just said, the formula is that A plus is equal to P transpose. And this is an M by M matrix. And A plus A, when you do things in the other order, is similarly, you get QQ transpose, which is an N by N matrix. So those are nice formulas telling you sort of how close A plus is coming to being a right or left inverse, which is to say these things could be the M by M or N by N identity, but maybe not. So let's look at an example. Let's take A to be this matrix 1, 1, 0, 0, 1, 1. We did this example in a previous slide or previous lecture. I'm not going to show all the details, but just write down a couple of steps. If that's A, then A transpose is a 3 by 2 matrix. And you conclude, after a little bit of calculation, that A plus turns out to be 1/3 this matrix, 2, 1, minus 1, and minus 1, 1, 2. So I'm going to skip that calculation, but you can check it. And so now if you multiply A times A plus, what do you get? Let's see. You get 2 plus 1 is 3, divided by 3 is 1. Okay, so that's the upper left-hand corner. And let's see, then you get, turns out you get the identity matrix. So if you multiply them in that order, you do get the identity. On the other hand, if you multiply them in the opposite order, where you do the A plus first and then the A, well, let's see, this is going to be a 3 by 3 matrix. And what's it going to be? Well, the first entry is going to be, looks like 2, or 2/3. And if you fill it out, it turns out that you get this matrix. So it's not the identity in the other order, and that's typical. That's a fairly general behavior of the pseudo-inverse. All right, well, I'm going to write down a couple of the properties of the pseudo-inverse. So we have an M by N matrix A, and its pseudo-inverse is N by M. So I can multiply A times A plus and get an M by N matrix, or A plus times A and get an N by N matrix. And I can hope that either one or both of these are the identity. So the fact is that if A has full row rank, so that means to say the rows of A are all linearly independent, which says that A actually has rank M, which is as big as it can be since it only has M rows. So that forces M to be less than or equal to N for that to happen. And then the statement is that A plus is a right inverse. A times A plus is the identity. On the other hand, if A has full column rank, which is to say it has linearly independent columns, well, that can only happen if the number of columns is less than or equal to the number of rows. And in that case, the identity works in the other order. A plus is a left inverse. And so if you put these two together, if A is N by N invertible, then A plus really is the inverse. So if there's both the right and the left inverse, then A plus is it. Now, you don't usually use it in that situation, but you might, and that gives the connection with the ordinary inverse. Okay, so last thing we're going to do is an application to linear equations. And let's look at an equation AX is equal to B, where A is, as usual, an M by N matrix, and so X is an N vector. and B is in Rm. And we're trying to solve Ax is equal to B. And I'm going to look at two opposite cases. So, for example, suppose that this matrix A had more rows than columns. So I'll kind of write it like this to indicate that. That is to say, n is less than m. So since I wrote that backwards, n is less than m. Since n is less than m, n is small, it could have full column rank. And since n is small, and so, and when that's the case, if it has full column rank, then we saw before that A plus is a perfectly good left inverse of A, which is good, because then we can just multiply this. We can take this equation Ax is equal to B, and we can multiply it on the left by A plus, and these cancel because A plus is a left inverse, and you conclude that you can solve this equation as x is equal to A plus times B, and that's an exact solution. So that's in the case when it has a full column rank, a small number of columns. The opposite case is when it has a lot of rows, a lot of columns and a small number of rows. When n is big, this time I really do mean n is big, then A plus is only a right inverse, and that's not really so helpful. You can't use that directly to solve this, but nevertheless, there is something interesting which happens here. You can't use A plus to get an exact solution the way we did in the previous case, but I'll explain that on the next slide. Here's the theorem. Suppose I give you an equation Ax is equal to B. A is, I'll remind you, m by n. X is an Rn and B is an Rm. Then if I take x is equal to A plus B, that is the least squares solution to this equation. It's very nice. It hands you the least squares, the best least squares solution. And I'll call this x star. And then, as usual, if you apply A to x star, well, that's giving you the projection of B onto the image of A.